Right, so what is the principle of mathematical induction? So as you'd obviously know, maths has a variety of tools that allows us to test and prove and evaluate different mathematical things we're given. And so the principle of mathematical induction is another one of these tools, but in this scenario, it specifically allows us to prove statements. So it allows us to prove like identities or propositional functions that are usually put in the form P of n, or you could also see it as like P of n like that. And it is given usually for a set number of integers where, say, for example, n is more than and equal to 1 or whatever. And so the principle of mathematical induction usually follows four main step processes. So in this video, we're primarily looking at the tape method, but you will see people use a very large variety of different words to name each of the steps, but this is just a really clear and simple one that's great to understand the actual process involved. And to test out this process, we're going to look at a particular scenario where Pn is, and it's important that every time you answer these questions you actually start with this clear statement of what you're trying to prove, where Pn is this plus ... recurring unknown number of values, and then 2n minus 1 equals 2n minus 1 for where n is more than and equal to 1. And now the principle of mathematical induction can be used in a variety of scenarios. So you can use it for trig, you can use it for evaluating matrices, for product rules and summaries and elements to different powers, and the list just goes on and on and on. And you'll see a few different symbols used for a variety of scenarios. So we've obviously, in this question we're looking at, we've got a full evaluated, just simple numbers, but you can also see symbols used to represent these sequences and series. Symbols that will look a little bit like that and that, where they were actually put values in, and it will look a little bit like you have, let me try and draw this as best as I can, you have like n like that, and then I equals 0, and then you'll have your actual sequence. And so let's get started with our first step. Unfortunately, and this really does help, is that the test stage of the tape induction process is the easiest. And so what we're going to do here is we're going to actually look at this as two separate parts. You've got your left hand side and the right hand side. Before we actually start this, I'm going to write the number 1, just to show that this is where we're starting. And you say, if n equals 1. So this is our test, is we're saying if, just for one random example, n equaled 1, and maybe you might have other scenarios where you might say n equals 2 or n equals 0 or whatever, but most of the time it's just if n equals 1, is Pn true? Comma, and what I'm going to do is I'm going to look at the left hand side first. So I'll write left hand side, and fortunately because of this series we only need to look at this section of it. What we'll say is 2 to the power of n, so that becomes 1 minus 1, so that equals 2 to the power of 0, and as you should hopefully know, anything to the power of 0 just equals 1. And then if we create a little divider here, we've got right hand side, underline that again, so we've got 2 to the power of m, so 2 to the power of 1, minus 1, which just equals 2 minus 1, which also equals 1. So then we can just say, therefore, P, and so instead of Pn, P1 is true. So very simple so far. And then we're going to go on to this next step, and this involves creating an assumption. So if Pk, so we're just using the letter K to represent this, if Pk is true, right, then, and I'm going to try and squeeze this in here so I can try and fit everything on this page as much as possible. We'll just say 1 plus 2 plus 4 plus ... plus 2 to the power, instead of n now, it will be 2 to the power of k minus 1 equals 2 to the power of k minus 1 there. And then so what we can do is we can start to test this and prove that pk plus 1 is true. So I'll write 3, And so we've got this that's definitely true, so we know one example is true. And we're saying, is it true for all scenarios? And so what we can do is if we know something's true for one scenario, then we can say, and this is what we'll do, is we'll say pk plus 1, because then we're saying if pk is any possible scenario, right, or any possible real value, then it must be true that pk plus 1 is also true, right? So, for example, let's just say, hypothetically, that k equals 4. Then if 4 works, because it's a real value, then 4 plus 1, which equals 5, should also work, obviously, right? So just get rid of these things, and let's give this a try. And so what we're going to do for pk plus 1 is we're going to put a very similar thing we did here. We're just going to put pk plus 1 instead. So we've got 1 plus 2 plus 4 plus plus 2 to the power, and I'll use brackets to make this clear, k minus, also k plus 1 minus 1, which equals 2 to the power of k plus 1 minus 1, and this is obviously for where n is more than or equal to 1. And then we can start evaluating it, and all we need to do is actually evaluate this left-hand side. So I can just state left-hand side, and we'll go 1 plus 2 plus 4 plus plus 2 to the power of k minus 1, which is just our general one there, and then the plus 2 to the power of k plus 1 minus 1, which is this one here. And we did this because this one is the one that is plus 1 more than that one. So then we can evaluate this by noticing something awesome right here, is that this is equivalent to this pk assumption that we made here. And so we said that that equal to this here. So we can actually evaluate this. And so we can say, therefore, and this is what makes it really simple, pk plus 2 to the power of k. And I've just evaluated this here because we know that obviously we can cancel out those two ones really simply. So that will be, obviously looking at that there, it'll be 2 to the power of k minus 1 plus 2 to the power of k. Now what we're trying to do is we're trying to actually get this equation into this kind of structure here. And so we can do something a little bit complicated slightly, is we can say, therefore, 2 times by 2 to the power of k minus 1, because if we were to add these two, that would obviously be 4 to the power of k, and so we can just change that up so it's 2 times 2 to the power of k. And then if I can try and squeeze this in, I might have to do this one. I'll say that 2 to the power of k plus 1 minus 1, because obviously in here that is technically to the power of 1, so when you multiply them, obviously the powers will just add, so just be k plus 1 like we've done there. And then we can notice that this is actually exactly in the form that that is, so we can literally just say which equals right hand side. Very simple. And so that's right there, that's tick for test there. We've got a tick for our assumption, which was here, and then we've also got a tick for proving that this equals to the right hand side in the end. And so now we've got to explain it. And so I've just got rid of the image so we have a bit of room to put this final statement in that's very important, which is the fourth step, which would go at the end of the thing, but obviously we don't have enough room. And so what it's going to follow this very clear statement, and it's going to talk about what we find. So we say, since P1 is true, and don't mind my writing, so this is our first part we did, and pk plus 1 is true, because obviously we can't say since pk is true yet, because that was an assumption, but the first part and the third part were both tests in a sense. Then we can say, so since p1 is true and pk plus 1 is true, and this is only whenever whenever pk is true, then Pn is true for all n is more than and equal to 1. And so what we've done here is we've utilised our two tests, and this second test was only on the assumption that this is true, but considering that both of those ended up giving the right result, then it is clear that we have proved that Pn is true for all of these select integers here. But this will change if obviously you've got other ranges you're given. So obviously it's quite a meticulous process in a sense to do the principle of mathematical induction, but fortunately it's quite a simple process of the 4 steps that you'll be following. But the main place you'll find it starts getting tricky is when you start implementing trigonometry and more complicated scenarios, where obviously it's still going to be easy proving for when 1 and just making an assumption, but where it gets hard is when you've actually got to evaluate it and try and prove that that equals to the right hand part of the equation. But it is worth noting that not all scenarios are true. It's very important to notice that not all propositions that you try to prove true will actually be true. And this is where it does get a little bit tricky, where you're trying to evaluate it and you don't know if either you're evaluating wrong and that's why you can't find an answer, or if it's true that maybe there is no solution. But the best thing you can do is practice as many different examples as you can to help build your understanding and actually recognize a lot of different scenarios and processes you can follow to prove that certain propositions are true.